small crisp session. Now, if you remember, I introduced the notion of self-induction to you in the last class. I told you what an inductor element is, what its property is, mentioned to you that essentially an inductor element is synonymous to what mass is in mechanics, inductor is in electricity. It's about electrical inertia that an element is capable of holding, right? Three elements that we've got introduced to: resistors, capacitors, and now inductors. L, a property, and depending on the geometry, the medium, the number of turns, these were the properties that go on to determine the inductance of an element. We spoke of an ideal inductor, a real inductor, one that has resistance in addition to the property L. It also has the property R. That's a real inductor, right? An ideal inductor has no resistance, right? Also, if you remember, if this was the property L of a certain element and there was a current I associated with it, and if there was no di dt, then the drop across the L would be 0. L is not opposed to I, it's only opposed to change in I, right? Because a change in I would mean change of flux associated with the coil. That is why the property L was opposed to only change of I, not to I, right? Like a mass is opposed to a change of velocity, not to a velocity. It will resist change of velocity. It's okay if it's moving with a certain velocity, it would want to continue with that velocity, right? That's inertia, right? But the moment you want to oppose that change, the moment you want to change the velocity, it would want to oppose that, right? That's what mass is. Now, I also told you that if you propose to change I and you initiate a di dt, propose change I, propose to initiate di dt, then that change is opposed with the help of what's called induced EMF. This induced EMF would be in such a sense that it would want to dilute the increased I. That's why it would want to drive a current like this. Such would be the polarity of the induced EMF, and the drop across the inductor element will be L di dt. We'll always take the drop, we'll always take the polarity such. The point where the current enters, we'll take that as the positive terminal. Where it leaves, we'll take that as the negative terminal of the battery. The drop, algebraic drop, will be L di dt. If di dt is positive, the drop will be positive. If di dt is negative, the drop will be negative, and therefore there would be an increase. But then you'll always say the algebraic drop is L di dt across an inductor element, right? Now, essentially then, if this is an inductor, we spoke about inductors in series and inductors in parallel, didn't we? Right? Now, if this is an inductor element, if this be an inductor element L, and there was no current initially in it, you want to build a certain current I naught in it. You want to build a certain current I naught in it. No current, you want to build it up to a current I naught in it. Now, every time you do that, let's say, starting from zero current, an intermediate state, there was a current I driven through the inductor element, right? I varied from 0 to I naught. This was the intermediate state of the growth of current through the inductor element. And like the way in a mass, the velocity does not change abruptly, the current also does not change abruptly, right? That's by virtue of the inertial properties that it has. Now, at this juncture, the induced EMF would be like this, and will be L di dt, would be the induced EMF. L di dt would be the induced EMF and such, okay? Now, realize, see one thing. When I want to raise this pen to a certain height, gradually without adding kinetic energy, then I'm doing work. I'm doing work against gravity. Gravity is trying to pull it down, and against the influence of gravity, I'm raising it. So I have to do some work to raise it to a certain height. To raise it to a certain height, against the opposition of gravity, I have to do some work. Now, once I have raised it to a certain height, of course, the work has been utilized to raise it to that height. But that work is recoverable also. That work in the form of energy is recoverable, which is the potential energy, right? Same thing here. When I'm trying to drive a current through this induced, that meets with an opposition, just like gravity. When I'm trying to raise it, it meets with an opposition, which is the downward force of gravity. This I also meets an opposition. So I'm doing work against this opposition. To be able to drive this current against the opposition, I'm doing some work. To be able to drive the current against this opposition, I'm doing some work, right? But when I'm doing that work, it's not like that work is getting dissipated. While I'm trying to build up a current, I'm trying to work against this opposition. When I'm trying to drive more and more current through this, I'm trying to build against this opposition of the polarity of the induced EMF. But then, successfully, when I'm raising the current to a certain value, I would have done a certain amount of work, right? There would be, let's say, another source of EMF that'll give that amount of energy. That'll act as a source of energy to drive current against this opposition. And once having done that, that work will be saved somewhere. That work will be saved as the energy in the magnetic field of this coil. Energy in the magnetic field of that coil will be the manifestation of that work, and it will be recoverable. That's the potential energy of the field. Whatever work I have done against this opposition to raise the current to a certain value, just like the case of gravity, then that work is recoverable. Its potential, where is it present? It's present in the magnetic field lines in the coil, inductor coil, right? Now, at a given instant, there is a current. That I am forcing against this opposition. How much opposition? These many volts of opposition. I'm trying to drive a current. That means the power that I require to drive a current I across this potential V would be V into I. The power in watts that I would require to drive a current against this opposition would be epsilon induced into I, would be the power that I require, right? Which is like L di dt into I is the power that I require, right? The energy required to overcome this opposition would be power into dt. In a small time dt, the energy required would be this into this. This would be the amount of work done. In a small amount dt, this would be the amount of work done, right? Which is like Li di. So the work done would be Li di. The total amount of work done, therefore, would be sum of all of this. That means where I runs from 0 to I naught. I runs from 0 to I naught. That's the total amount of work done, right? Which turns out to be half Li naught squared. That means to build it up to a current level I naught, this is the amount of work that I did against the opposition of the induced EMF, right? And this energy, this work done does not go waste. It's saved somewhere as potential energy of the magnetic field lines in the coil. Potential energy of the magnetic field lines in the coil. Magnetic energy. That will be the magnetic energy. So half Li naught squared is the energy stored in the inductor element at an instant when the current associated is I naught. When the current associated is I naught, the energy stored in the inductor element is going to be half Li naught squared. And it's recoverable. I can cause this energy to manifest itself in other forms, which we will see down the line. Clear? Does it make sense? Half Li naught squared, therefore, is the energy associated with an inductor element. Now, so this was, in the sense, I bypassed all stages in the growth of the current from 0 to I naught. Whatever I did not actually reveal to me how the growth of current took place, how current varies as a function of time during this growth of current from 0 to I naught. That fact has not yet been revealed by this work energy calculations. Clear? So it becomes important for us to even figure that out. So the next that we are going to do is how the current builds up in an inductor element. Obviously, if a current has to build up, there has to be a source of energy which would be in the form of a certain battery connected to an inductor element, a battery of EMF epsa. This half Li naught squared has to be sourced from somewhere. So that would be the battery from where it will be sourced, right? So let's think of an inductor element connected to a source of EMF, and we propose a growth of current commensurate. Of course, we'll talk of a real inductor. When we talk of a real inductor, that means it will have a resistance also. So it will have two aspects associated with it. There would be a L and there would be a R, right? So there would be an L and there would be a R. This entire thing is the inductor element, right? And this would be a battery, say EMF epsa. Battery, EMF epsa, switch. Initially, at time t equal to 0, there was no current. The switch was open and there was no current through the inductor element. When I activated the cell, when I activated the switch, then the current was 0 at time t equal to 0, but there was a non-zero di dt associated. This guy had proposed to raise the current. So what this does is it produces a di dt, a non-zero di dt. Even though I was 0, di dt was not 0, therefore the growth gets initiated. The growth of current gets initiated because of a non-zero di dt prevalent in the circuit. Okay. Now, current starts to grow. At a certain instant, let's say the current was I. We are only pretending that we knew this. And there was a rate of change of I with time associated with the circuit. Now, at this instant, from instant to instant, at every instant, I could apply KVL to the loop. So I choose to apply KVL to the loop at an instant of time t. When I do that, then, okay, what's the drop across the inductor element? L di dt. Always, the drop is L di dt. It could be a positive drop or a negative drop. What's the drop across the resistor? IR. So let me apply loop and apply KVL. So then L di dt plus IR must be equal to epsa. That's applying KVL to the loop, right? So now I get di by epsa minus IR is dt by L Let me integrate both sides. At time t equal to 0, I was 0. At time t equal to t, say I became I. So this will give me I as a function of time. Now, easy to integrate. I could multiply with r, minus r, and cause the numerator to become the derivative of the denominator. So a minus r here, right? Then on integrating we get log epsa minus IR divided by epsa is minus RT by L, or epsa minus IR by epsa is e to power minus T into R by L, or I equal to epsa by R 1 minus e to power minus T divided by L by R. Now, this L by R has units of time, right, and is referred to as time constant of the LR circuit. This is called a LR circuit. This is a typical LR circuit, and L by R is the time constant of the LR circuit. L by R is the time constant of the LR circuit. So, I as a function of time is like epsa by R into 1 minus e power minus T by tau. Tau is L by R. Now, notice some very simple things here. At time t equal to 0, you can see the current was 0. That means when I activated the switch at time t equal to 0, there was no current at that instant of time, which means the whole thing must have behaved like infinite resistance. L must have behaved like infinite resistance, yes or no? L must have behaved like infinite resistance. So that means when there is no current associated with the inductor element, when there is no current associated with the inductor element, and an alien comes down and says, I want to initiate a current in this, he proposes a change, then that's dealt with a lot of vehemence, a lot of opposition, infinite. The inductor element is like equivalently one of infinite resistance, at time t equal to 0, when there was no current driven through the inductor element, when there was no flux associated with the L, right? So L behaved like an infinite resistance. Now, after a very long time, realize that I becomes equal to epsa by R, because this will become 0, right? That means after a very long time, current became epsa by R and stood there. So this was steady state conditions for the LR circuit. This was referred to as the steady state for the LR circuit, steady state current. That means at time t equal to infinity, di dt must have become 0. There was no further rate of change of current with time. You can see that. See, if I differentiate I with respect to time, epsa by R into minus 1 by tau e to power minus T by tau. Yes or no? Plus. This is how, if I differentiate I with respect to time, do you see that at t equal to infinity, di dt became 0? That means there was no further rate of change of I with time. So steady state conditions were then reported on the circuit. I stayed put at that value and equal to epsa by R. Under steady state conditions, therefore, the current driven through the circuit was epsa by R. That means it was as if the inductor element was not even there. At t equal to infinity, it was as if there was no inductor element. It's as if there was just a resistor, R. That means the inductor element behaved like zero resistance at time t equal to infinity. Under steady state conditions, so under steady state conditions, the inductor element behaves like zero resistance. The inductor element behaves like zero resistance under steady state conditions. Di dt will become zero. Got me kya? Huh? Everything can be applied. Just that, you know, we've not, all the results that you have learned, you could apply. You can apply Thevenin's theorem to all electrical elements, right? Now, the graphical variation of I with time. At t equal to 0, current was 0, but there was a non-zero di dt. There was a non-zero di dt, right, at time t equal to 0. And then current grew, but at a decreasing rate. Di dt, as t increases, di dt becomes smaller and smaller. Do you see that? As t increases, di dt will become smaller and smaller. So the curve will become flatter and flatter. The curve will become flatter and flatter because the slope of the curve decreases. So the curve becomes more and more flat. This is how the curve grows. After a very long time, the current reaches a steady state value equal to epsa by r. Current reaches a steady state value equal to epsa by r. So di dt is maximum initially, and then less and less of di dt. That means the opposition decreases. बेचारा inductor element सोच रहा है यार current अब flow ही कर रहा है, ठीक है. So the opposition is measured by di dt, isn't it? L di dt. So opposition that the inductor offers is measured by di dt. तो वो देख रहा है, शुरू में देखा साला कोई current नहीं है, कोई current घुसाने का कोशिश कर रहा है, तो it offered maximum di dt. It got wild. Right? But dhire dhire when current started flowing, it said, all right, yaar, I will have to resign to fate. Let me mellow down. So it offered less and less of di dt. It started accepting life the way it was. Like normal human beings, the inductor element behaved. Right? Hai na? When you enter class 11, you know, that sudden change bothers you the most. Right? And you offer resistance to that change. But with time, as time passes, you begin to resign to the way things are happening around you, the way I am teaching, the way anyone else is teaching. Sala ye to aise hi karega, jaane do. Right? So you are also like an inductor element. And I am that epsa. And the school is this R. It gobbles down the energy. This LDIDT, though you are offering, despite the resistance, you are building up some potential energy. And when you go to the school, it's dissipating I squared R. Okay? Whatever I am supplying here to you in the form of energy, part of it is getting saved here as half Li squared. And then you go to school after this, they dissipate some of it. You are left with less amount of energy, and I could do nothing about this Joule heating. This was Boole heating. Okay, got me? Okay. Now, steady state. Now, so unlike the capacitor element initially behaved like zero resistance. When it was uncharged, it behaved like zero resistance, but under steady state conditions, as it gathered more and more muscle in the form of charge, it acquired a steady state charge, and then it behaved like infinite resistance, prevented any further accumulation of charge, prevented any further flow of current through a branch in which it was connected. So the inductor element just behaved the other way around. Okay. And of course, as you can see, at t equal to tau, this will become 1 by E. 1 by E is 0.37 roughly. So this will become 0.63. So this will become 63% of the maximum current. In a time t equal to tau, it becomes 63% of the maximum current. That good. So that's the growth of current in the LR circuit. That's the growth of current in the LR circuit, right? That's how it grows. Right? Now, if I have set up a current I naught in an inductor element, I would also want to sometime withdraw that current, right? Say there is an inductor element, there is a resistance R, inductor L, resistance R, and I have been able to set up courtesy EPSA a certain amount of current I naught in the loop. This is the switch, etc. Right? Now, one difference between the inductor element and the resistor is that in a resistance, current can die out instantly. If you open the switch, the current will die out instantly. But in an inductor element, because of its inertia, the current will not die instantly, right? In 0 seconds, can you reduce the velocity of a mass from 1 meter per second to 0 meters per second? You cannot, right? You cannot. In 0 seconds, can you reduce its velocity by 1 meter per second? You cannot, na? Same thing. An inductor element, an abrupt change is prohibited. Because it has an inertia. It has an inertia, right? The killing all the current in it is like withdrawing all the field lines. This energy has to immediately get dissipated. However, see, if you propose to, if there is a mass moving with 1 meter per second, and in 0 seconds you reduce its velocity to 0, the mass will experience what's called a jerk. That's harmful to a system, let's say. That's harmful to a mechanical system. Producing a jerk, trying to reduce the velocity to 0 in 0 seconds, produces a jerk on a mechanical system. It's harmful for the mechanical system. Theoretically, let's say you can do it also. Okay, same way. Say if you abruptly open the switch here, and say I'm going to kill the current instantly, what really transpires is, across this switch, there would be a potential difference, there would be a spark generated, there would be heat light associated, the current might die to 0 instantly, but it's harmful for the electrical circuit. It's harmful for the electrical circuit. It's not a good thing to unnecessarily produce heat and light and sound in an electrical circuit, right? So it's not advisable to withdraw this current by deactivating this switch. Because if you deactivate the switch, you run the risk of damaging the electrical circuit. You run the risk of damaging the electrical circuit. Right? So you don't want to do that. What you then want to be doing is, you want to gradually withdraw the current I naught from I naught to 0. That's what you want to do. So what's done is, in a LR circuit, withdrawal of current takes place with the help of another ancillary circuit which is connected to it, in which there is a resistance, we'll call it the bypass resistance. Now, the current through the inductor element, the current through the resistance will die instantly because the switch is open. But the current through the inductor element is not going to die instantly. It will circulate through this loop. It has a passage through this loop. There is an energy half Li naught squared here in the inductor element that will keep getting dissipated across the resistance in the form of Joule heating. So this half Li naught squared in a period of time will get completely consumed by Joule heating across the resistance. You know what I'm saying? And it's not going to happen right away. Right? It's not going to happen right away. It will take a little while for complete withdrawal of this current. So there would be a gradual decay of current. There will be a gradual decay of current from I naught to 0 through this bypass circuit, right? So let's see the characteristic of the decay of current through a LR circuit when an initial current is I naught and the resistance is small r. Let's see how the current gets withdrawn, how the current gets decayed through this loop. Clear? Okay. So very clearly, what's happening is more and more of this energy is getting dissipated across this, because to drive a current through R, you need I squared R. Where will it come from? It will come at the behest of the energy half Li naught squared here. So this half Li naught squared will diminish, will get depleted, and will appear as Joule heating across this. So current will decrease. So t seconds from this instant, let's say the current becomes I. T seconds from this instant, let's say the current becomes I. In this loop. I is I naught and we want it to decay to 0, right? If there is an I is decreasing with time, so there is a didt associated with the circuit, right? So the drop across the inductor element will be L didt. That's a drop across the inductor element, and then the current circulates like this. The drop across the resistance would be IR. Let me apply KVL to the loop. Let me apply KVL to the loop at this instant of time during the decay. So then the drop across this L didt plus IR, that must be 0. Right? Di by I is minus dt R dt by L. Right? Integrate both sides. At t equal to 0, I was I naught. At t equal to t, let's say I became I. What do you say, bhai? Clear, na? Integrate this. Log I by I naught is minus R by L into t. I then becomes I naught e power minus t divided by tau, where tau would be L by R. Tau would be L by R. That's a time constant for the decay. That's a time constant for the decay. Okay. So the decay takes place exponentially. It's fast. It's a fast decay. Exponential decay is a fast decay, but it's not abrupt anyways. We do want a quick decay. That's happening here. Quick decay. That's happening here. So I versus t. At t equal to 0, I was I naught. It decays at t equal to tau. It becomes 37% of I naught, as you can see, because 1 by E is 0.37, so 37% of I naught, and the current decays gradually, not gradually, fast, but not abruptly, to 0. How's that? Does it make sense to all of you? Okay. Now, one more fact that I want to mention for inductors. You know, the inductor coil L, you know, this region could either be air or sometimes there could be some other medium in it. For example, there could be what's called a soft iron core. That's a soft iron core. So the medium is different now in the inductor element, right? And L depends on the property of this medium. L will also depend, in addition to the geometry of this coil, it will also depend on the property of the medium. Clear? Now, let's say with the core inside, if the inductance was L1 and at a certain instant the current was I1, right? And let's say you could change L by withdrawing part of the core out. Let's say, you know, you could have had a situation where, say, you could have pulled out by some mechanical means, you pulled out the core to a certain extent. So part of the coil has a certain medium, part of it is air. So the inductance will change. So it could be treated like a variable L. A variable L is then in the offing for you. So let's say L becomes L2 by some means, by pulling the part of the soft iron core out, right? And the current was I2. The current was I2 produced then. Because L changes to L2, let's say current changes to I2. Just like the conservation of linear momentum in absence of an external force, the total linear momentum of the system is conserved, right? So there they had mass into velocity. Here you have L into I. Instead of M into V, you have L into I, right? So with this sudden change of L, what remains preserved is L into I. L into I is the flux associated with this, right? L into I is the flux associated with this. So what's the way I2 will respond is that L1 I1 will be L2 I2. L1 I1 will be L2 I2. If L is changed to L2, I will change to I2 such that L1 I1 will be L2 I2. It's synonymous with the conservation of linear momentum in mechanics. It's not like half Li squared will remain constant here. You might think, "Kya re sala, energy क्यों change हो गया?" Because half L1 I1 squared is not half L2 I2 squared. Energy क्यों change हो गया? Energy is changed because in order to pull this out, a certain amount of work had to be done. Right? That's why the energy changed. You know? Got me? Now, so this was a quick one on what's referred to as growth and decay of current in LR circuits. Let's look at now a circuit in which there is a pure inductor and an ideal capacitor. Let's look at a circuit in which there is a capacitor and there is an inductor. No resistor, no dissipative element. No dissipative element. Both L is a conservative element because this half Li squared is available for use. Q squared by 2C is available for use. These are not dissipative. They don't hog up energy. They might consume energy which they can store and make available at some point of time as is deemed fit. Right? So let's say I have a circuit in which there is a L and there is a C. Okay? Pure inductor, no dissipative element. Pure inductor will not have resistance in it. And there is a C. Now when I connect them this way, what happens? Kaach kola, nothing happens. Nothing happens if I connect jhoot moot mein. Right? Nothing will happen. Nothing will. Bird. Let's say if there was a capacitor that was pre-charged to a value Q0, then there is locha. Because then, these two plates are at different potentials. So there would be something that would want to drive the current this way through the inductor element, and this fellow would want to oppose that. So this will produce a DI/dt in the circuit. This will produce a DI/dt in the circuit, right? So there is now a current characteristics associated with it. If a pre-charged capacitor is connected to an inductor in a loop, then there would be a current characteristics that would be associated with this circuit, right? So this charge varies with time. This charge therefore varies with time. Theoretically, let's say this was the capacitor. At a certain instant of time, the charge was Q. L, etc. And let's say there was a current I like this through the circuit. And there would then be a DI/dt, so there would be a drop L DI/dt across the inductor element. I can apply KVL to the loop, right? So when I apply KVL to the loop, I have like a L DI/dt plus Q by C equal to 0. But the rate at which this deposition changes with time will measure current I. So I will be measured by dq dt. So this I can write as dq dt, which then renders as d2q dt2 equal to minus q by c. क्यों भाई, है ना? Right? So d2q dt2 is minus 1 by LC q. Right? It's the same as the equation for the oscillator, simple harmonic oscillator. d2x dt2 is minus omega squared x, isn't it? Instead of q, instead of x, you have q. How about it? No? The solution to this was x equal to, let's say, a cos omega t plus phi. In this case, the solution would be q equal to some q naught cos omega t plus phi would be the solution to this equation. Right? Here is an amplitude. Here you have an amplitude of x. Here you have an amplitude in q. Q is a function of time, exactly the way x was a function of time. The differential equation doesn't know how to distinguish between x and q. If it has popped out a solution for this as x equal to a cos omega t plus phi, then it will pop out a solution for this as q equal to some q naught cos omega t plus phi. Yes or no? Right? So then q as a function of time becomes q naught cos omega t plus phi, where the new omega would be such that omega squared is 1 by LC. है ना? Omega squared is 1 by LC, so omega would be 1 by root LC. Right? And no matter what this omega is, omega t must be radians. Omega t must always be radians. So this omega also is radians per second. Because omega t is radians, this omega must be radians per second. So the dimensions of 1 by root LC is radians per second, is radians per second. Clear? Very good. Now this is the phase constant phi. At time t equal to 0, q was q naught. है ना? At time t equal to 0, q was q naught. Because we started with a pre-charged capacitor q naught. And realize that could have been the maximum charge ever. So this must, as expected, in fact, you know, q, even if I didn't do this, say A cos omega t plus phi, then I could have figured out that Q, this A must be Q. The maximum Q is Q naught. The maximum Q possible is Q naught. So this must be Q naught. You know? This must be Q naught. And phi must be 0, because at t equal to 0, Q is Q naught. So phi must be 0 given this. So charge varies with time as Q naught cos omega t. Now, this is an intermediate state of the circuit. This was an initial state of the circuit. In this state, the current was 0, right? And charge was Q naught. What was the magnetic energy? Energy in the magnetic field? 0. 0, na? Right. Therefore, the total energy here was Q naught squared by 2C. Now, when you come down here, what's the energy in the inductor? Half Li squared. What is the energy here? Q squared by 2C. Which means the energy here is purely electrical. Energy here is electrical as well as magnetic, And you also realize that means now where did this magnetic energy come from? It must have come at the expense of the electrical energy, right? So part of the electrical energy has manifested itself as magnetic energy, half Li squared, in the intermediate state. Now Q is Q naught cos omega t, right? At t equal to 0, charge was Q naught, and the total energy was electrical. Total energy is electrical. Electrostatic energy in the between the plates of the capacitor, energy in the electric field. Okay. Now at t equal to pi by 2 omega, Q will become 0, isn't it? And what is I? I would be minus Q naught omega sin omega t. So when omega t is pi by 2, this will become minus Q naught omega. So Q is 0, electrostatic energy is 0, and the total energy in the magnetic field will be half Li squared. Yes or no? That means the energy becomes purely magnetic. This purely electrostatic gets converted into purely magnetic in how much time? In a time equal to pi by 2 omega. In a time t equal to pi by 2 omega, there is complete translation from electrostatic energy to magnetic energy. In fact, again pi by 2 omega seconds later, it will get converted into purely electrostatic. That means this is an important number for a LC circuit. This is an LC circuit. In a time equal to pi by 2 omega, the energy gets converted from purely electrostatic to purely magnetic, or vice versa. This is an important number for the LC circuit, pi by 2 omega, right? In this time, the energy gets completely converted from electrostatic to magnetic, or vice versa. Energy is oscillating. Absolutely. You're right. Energy is not oscillating. Total energy is constant. It's shuttling between the capacitor and the inductor. It's, yes. No, it's both potential energy in this case. There is, you can say half Li squared like kinetic energy kind of a thing. But that's actually again potential energy in the field. So, so this is an important number for the circuit, pi by 2 omega. and this is the energy in an intermediate state. It must be the energy in any other state, so it must be the energy initially that the circuit comes with. Okay, Q naught squared by 2C. This must be Q naught squared by 2C. So if at some instant of time someone gave you what the Q is, then you could have calculated I from total energy conservation. Total energy conservation. Right? In fact, as you can see, the total energy at any given instant of time is half Li squared plus Q squared by 2C. This E is time independent. I varies with time, Q varies with time, but E is time independent. So dE dt must be 0. dE dt must be 0. Is it not? So if dE dt is 0, you get Li di dt plus Q by C dQ dt. That must be 0. Right? Hey, but dQ dt is the same as I. So dividing by I. So you get L di dt plus Q by C equal to 0. Hey, which was the original equation that we wrote, which was essentially KVL through the loop, isn't it? Which was essentially KVL through the loop. So that KVL essentially is about energy. Essentially about energy. So this is referred to as an oscillatory circuit. An oscillatory circuit. Energy oscillates between energy in the capacitor versus energy in the inductor. So it's an oscillating circuit. Q oscillates as Q naught cos omega t. Q oscillates as Q naught cos omega t. Right? Now, if there was a resistance in the circuit, then what you will get is damped oscillation. That resistance is like, if you had a typical simple harmonic oscillator and there was air resistance, then its amplitude will go on decreasing. Right? So there also the maximum charge on the plates of the capacitor, which was Q naught all the time, that will go on decreasing. The amplitude of Q will decrease. That will behave like a damped oscillator. If there was a resistance in the circuit, you will have damped oscillation, and the maximum, so the total energy will decrease. The total energy will not remain constant because part of the energy will keep getting consumed in the resistance as Joule heating. Right? And that will manifest as the decrease in the amplitude of Q. The maximum Q naught goes on decreasing with time. That's going to be a function of time. Is that all right or not all right? But we don't have to bother about a LRC circuit. That will be a LCR circuit. This is a LC circuit, ideal oscillator. That's what we'll look at. Now, see, when I started with this concept of L, I told you there was a current in the coil, in the element, and we changed the current through the element, the flux through the element changed. d phi dt, which measured the EMF produced. d phi dt measured the EMF produced. Minus d phi dt was crap, didn't help in anything. Okay. Now, let's look at the flux changing through a loop. But this flux is not produced. See, in the earlier case, we said, well, the current through that loop changed and the flux through that loop changed. But now what we'll imagine is the flux through a loop produced by a current through some other loop. Say there was loop 1, and there was loop 2. In general, non-coplanar, let's say. There was a current in 1, call it I1. Now this current produced a magnetic field in the surroundings. So there was a flux associated with this. See, those magnetic field lines penetrated through loop 2. It produces B at different points. So there were magnetic field lines. So those magnetic field lines intercepted the loop 2, and there was a flux associated with loop 2 because of current in loop 1, right? So there was flux associated in loop 2 because of current in 1. If you double the current in 1, then the magnetic field at every point in the surroundings will get doubled, and therefore the flux associated with loop 2 will also get doubled. বুঝতে পেরেছিস? আমি বলছি যে if I double this current I, then Biot-Savart law mu naught by 4 pi I dl cross R by R cube, the B gets doubled at every point. So if the B at every point gets doubled, the flux associated with this loop will also get doubled. That means phi through loop 2 will be proportional to current through loop 1. This is flux not because of its own current, but because of the current in 1. And the flux through loop 2 will be proportional to the current in 1. And the flux through loop 2 will depend on what all? For a given I equal to I1 through loop 1, the flux through loop 2 will depend on, number 1, the geometry of the two loops, will depend on the geometry of the two loops. Will depend on their relative orientations. Medium and number of turns. This is what it would depend on, flux through loop 2 because of current in loop 1, right? Now flux through loop 2 then would be, say, a constant M to 1 into I1. This constant M will depend on these factors, and is called the coefficient of mutual inductance of 2 with respect to 1. Mutual inductance of 2 with respect to 1. Right? It's called the coefficient of mutual inductance of 2 with respect to 1. Now, if I change the current in 1, then it affects the flux in 2. Therefore, there would be an induced EMF in 2. How do you calculate the induced EMF in 2? The induced EMF in 2 would be calculated as d phi 2 dt. Would give me the induced EMF in 2, and that will be M21 di1 dt. That's the induced EMF in 2 because of change of current in 1, which resulted in change of flux associated with 2, and therefore from Faraday's law, the induced EMF in 2, right? Now reverse the roles. This was loop 1, same loop, and this was loop 2, same loop 2, same relative orientation, same geometry, everything remaining the same. I'm not tinkering with this, intact, but what I do is I drive a current into. This time I drive a current into, hypothetically imagine that a current is being driven into, and that will produce B in the surroundings, which will cause B lines to pass through 1. So there would be a flux associated with 1. So flux in 1 will be proportional to current in 2. And flux in 1 then could be written as M12 I2, where M12 is the coefficient of mutual inductance of 1 with respect to 2. It's called the coefficient of mutual inductance of 1 with respect to 2. And if I change the current in 2, it will change the flux in 1. Therefore, there would be an induced EMF in 1. So, epsilon 1 would be M12 di2 dt. Differentiating phi 1 with respect to time will give me induced EMF in 1, right? Now, a result that I am going to state, but the proof of it is beyond the scope of things that you know, beyond the scope of mathematics that you know. This is called the theorem of reciprocity. Theorem of reciprocity. Which essentially says that M12 will be the same as M21. Coefficient of mutual inductance of 1 with respect to 2 will be the same as coefficient of mutual inductance of 2 with respect to 1, and each will be referred to as M, the mutual inductance of the pair. It will be referred to as the mutual inductance of the pair. Of the pair of loops. It will be a property of the pair. It will be a property of the pair of loops. Coefficient of mutual inductance of the pair. It's not possible for me to give you a formal proof of this, but we will use this result very frequently, right? That means in order to calculate M, either I can, so imagine current in 1, calculate the flux in 2 and divide phi by I, and I can get M. Or I could just reverse the roles. I could drive a current in I, obtain the flux in 1 and divide this by this. That will also give me M. In either case, I am going to get the same number. That's the important thing. That's a theorem of reciprocity of mutual inductance. Just to get you inducted. One thing, of course, let me also tell you that if the pair has a property M, but each one of these loops have independently an L, right? They have a self-inductance, they have a property L inherent to them, and they have a mutual property M, right? Again, you know, not that I am going to use this result, but let me tell you that M is actually related to L1 and L2, their self-inductances, as some K times root L1 L2, where K is called the coefficient of, is called the coupling constant. And it has a value from 0 to 1. It has a value from 0 to 1. When K is 1, the pair of loops are said to be perfectly coupled. When K is 1, they are said to be perfectly coupled. Clear? Now, say there are two concentric coplanar loops. Concentric coplanar loops. One chotu, one bada. Let's say this is a bacha loop, this is a barb loop. Okay, and A much smaller compared to B. That means the chotu loop is really chotu. Okay, very chotu. They have a common center O. Okay, and for this pair of loops I want to calculate M, the coefficient of mutual inductance, or the property M I want to calculate, where B is much larger compared to A. Now to calculate M, what I would do, essentially mentally imagine, right? To calculate M, I would just mentally imagine I and phi. I would mentally imagine, hypothetically imagine a current through one and obtain the flux through the other one. Then phi divided by I will give me M. Now that choice has to be judicious. Suppose I did the following. See which one would make sense. Suppose I drove a current in one, right? And I had to calculate the flux through the outer loop. That means for a current I, this current I will produce in this region a magnetic field, will produce in this region a magnetic field. There would be a flux associated with it. There would be a flux associated with it. Now, realize that this is really small, really small. This then would be a region of non-uniform magnetic field, because if I look at any element, let's say a dl and a r, for example, in this annulus, then dl cross r would be into the plane of the board. If I look at a point, that means the flux in this annulus would be into, but this is also a part of the bigger loop. So the flux inside, if I look at an r here, then this dl cross r would be out of the plane of the loop. So for this sense of the current, in the annulus, the flux is into, in this region, the flux is out. So in this entire region, part of the region there is flux going into, for this sense of the current, and part of the flux is coming out. However, I can tell you there is a net flux going in, because this part is much bigger compared to this. So the region in which the flux is coming out is much smaller compared to the region in which flux is going in. So I can tell you, if this is the sense of the current, the net flux in this region must be into the plane of the board. That's a good estimate. Okay, but that's not important right now. What is important is that different points in this region are at different distances from this current carrying element. Therefore, this would be a region of terribly non-uniform magnetic field. Non-uniform magnetic field. Now, in a non-uniform magnetic field, then it's going to be a tall order to calculate the flux associated with that region, right? It's going to be tough to calculate the flux associated with that region. Therefore, and then phi divided by I then could be a tough task. It will give me M. I might work on it laboriously and get the value of M, but it could be really difficult. It could be really difficult, right? So this doesn't seem like a practical thing to do, driving a current in this and calculating the flux through this. What we do is, in contrast, say I drive a current through the bigger one, right? Now if I drive a current through the bigger one, then this current carrying loop at the center produces a magnetic field which is mu naught I by 2b. Mu naught I by 2b is the field that it produces at the center of this loop. You know this result, right? Magnetic field at the center of a circular loop. And this field is coming out of the plane of the board. You know? It's coming out of the plane of the board. Now, this is a really chotu loop. So all points on this are very close to O. So can I not practically imagine that the field at every point in this region is almost the same as field at O? Right? So that means, if this could be imagined to be a region of uniform magnetic field with B being B naught going into the plane of the board, out of the plane of the board in this case, B would come out of the plane of the board in this region, right? So there is flux coming out, and easy to calculate that flux because it's simply going to be B naught into this area. B naught into this area, that's going to be the flux coming out in this case. So what's the flux associated through the smaller one? The flux through the smaller one would be mu naught I by 2b b into the area of this pi a squared. So this is the flux through one with the current through the other one. So phi divided by I will give me the property m for the loop, will give me the property m for the loop. So m for the loop is phi through the smaller one divided by I through the bigger one, which then turns out to be mu naught by 2b into pi a squared. That's the coefficient of mutual inductance for this. See, this m I can calculate in any manner I choose, driving current through one and calculating flux through the other one, right? Now, this will be a property obtained one time for this pair of loops. And it's my choice as to how I should calculate this, right? But say, there is an actual situation of the following kind. There is a current driven through the smaller one, same pair, which is say 3t squared is the current as a function of time through the smaller one, right? I want to calculate so this is varying with time. So the flux associated with the bigger loop is varying with time. Therefore, there must be an induced EMF in the bigger one. Now, to calculate the induced EMF in the bigger one, I would know the flux. I should know the flux through the bigger one as a function of time and differentiate that with respect to time. That will give me the induced EMF through the bigger one, right? Now, I have calculated m by reversing roles, by driving a current through this and calculating the flux through this. But the same m could be used for the reciprocal situation, right? So then the flux through the bigger one then would be, the flux through the bigger one would be what? Mi. The mutual inductance calculated howsoever, m into I. Right? So the EMF induced in the bigger one would be d phi dt, which is m di dt. Right? Which is m I have already known, di dt is 60. That's induced EMF. That's induced EMF. चलो उसका sense निकालते हैं. Let's figure out the sense of this induced EMF. So this is the magnitude of the induced EMF in the outer loop, bigger loop. The direction of this induced EMF. Okay, so when this current is increasing, first of all, like I showed you, if this was the sense of the current, then at points here, there would be field going into. At points here, there would be a field coming out. But the net field would be into. Right? dl cross r. Right? Now, if I increase I, the flux going into the plane is increasing. So, and this effect is prominent, more prominent compared to this effect. Because this is a smaller region. So, there is, on an average, there is greater flux going into the plane of the board. Kya? Hai na? So, if there is greater flux going into the plane of the board, that must be opposed. That means some flux lines must be thrown out. Now, how can some flux lines be thrown out? If the induced current flows this way in the outer one, if the induced current, no, this way in the outer one, if the induced current flows this way, then it will throw some flux lines out so as to partially dilute more flux lines going in. Lenz's law, right? So, the induced EMF here must have this as its polarity, so that it drives the induced current this way. You know, this must be the polarity of the induced EMF. Now tell me, if I had written minus d phi dt, how on earth could you compute the sense of this induced EMF? Minus d phi dt will not give you direction. It will make you directionless. Okay? You have to obtain that from first principles. Look at the situation, examine, investigate, and obtain the sense of the induced EMF. That's what you need to be doing. Right? Now, suppose the loops were such that their axes were perpendicular. See, this is the axis of this loop, chotu loop, and this is the axis of the bigger loop, right? Aisa hai. This loop is like this, and this loop that you see is like this. Okay? Now this is a pair where their axes are mutually perpendicular. In the earlier case, they had a common axis. Then when they were concentric, they had a common axis. Now their axes are perpendicular. Okay? I hope you realize how this is oriented this way. This is this one, like this. Jiska axis would be like this. This is like this, whose axis is like this. And I want to calculate for this pair the coefficient of mutual inductance. Hey, I drive a current, let's say, through the outer one and calculate flux through the inner one. Perfect, right? Because, see, all the flux lines associated with this are coming this way, right? Are coming this way. So the flux associated in this direction is 0 through this one. So phi is 0 when I is I. So M is 0. Nahi kya? I'll explain again. Dekho. See, if there is a current I like this, in this plane, the flux is coming out of the plane this way. Okay? B lines are like this. But I want to calculate the flux through this. Notebook do. Flux lines तो ऐसे आ रहा है बाहर, पर ये जो लूप है ना ये ऐसा है. तो व्हाट्स द फ्लक्स दिस वे? 0 है ना, कोई फ्लक्स, बिकॉज फील्ड लाइंस तो सारा रनिंग पैरेलल टू दिस. दे आर नॉट पेनिट्रेटिंग दिस लूप, सो देयर इज नो फ्लक्स पेनिट्रेटिंग दिस लूप, है ना. सारा फ्लक्स लाइंस ऐसे जा रहा है. So no flux through this. So flux through this is 0. So coefficient of mutual inductance will be 0. Flux through this is 0. So M is 0. ठीक है? Suppose, so this was this loop like this and this loop like this. ठीक है? Suppose instead of the loop being like this, it was at an angle theta this way. So what you will do is resolve this area as A cos theta and A sin theta. So through that A cos theta we will do the calculations like we did. Through that A sin theta there would be no flux associated. So that will not participate in M. It will be A cos theta which lies in this plane, coplanar with this, that will participate in the flux. You know? Got me? In order to calculate M for a pair of electrical entities, it's not important that both have to be loops. Sometimes only one of them is a loop. For example, one could be a long current carrying wire, and one, let's say, could be a square loop this way. कुछ नहीं है, A B C D से. A units by B units and say at a distance X naught units. This nearer end is at a distance X naught units. This is a loop. And for them, for this pair, I want to calculate M, the coefficient of mutual inductance. So now I don't have a choice here. The current will be through this because I can't calculate flux through this. So I'll have to calculate flux through this only. So I'll mentally imagine I through this and calculate flux through this. Now this is a region of non-uniform magnetic field, but not difficult to deal with. What we can do is, I can imagine rectangular areas of this kind. This one at a distance x and of thickness dx. This strip has a magnetic field mu naught I by 2 pi x is the magnetic field associated with this, right? And into area, this is dx into b. B into dx. That's the flux associated with the shaded portion. The total flux associated with the shaded portion would be when x changes from x0 to x0 plus a. X changes from x0 to x0 plus a. That's going to be the flux associated with the loop when a current I flows through the wire. So which is like mu naught IB by 2 pi log x0 plus a divided by x0. So the coefficient of mutual inductance is going to be phi by I, which is mu naught B by 2 pi log x0 plus a by x0. So if there is a current I that's here and there is a di dt, then there would be a d phi dt, which would be like a m di dt. M is known to us, m di dt. If I is increasing with time, see, this current is producing field going into the plane of the board, isn't it? dl cross r. Now if I is increasing, there will be more field lines going into the plane of the board. So the driven current, induced current, must throw some field lines out. That can happen if the induced current is like this. है ना, ताकि some field lines are thrown out, and therefore the sense of the induced EMF must be this minus plus epsilon induced is like this. What do you say to this?